Hello, and welcome to today's webinar on Project Panama, Part 3. This is the third webinar in our series of 3 webinars on Project Panama. My name is Jenny, and I will be your host today. Before we go ahead and get started, I have a few housekeeping items. Today's session is recorded, and we'll be sure to send the on-demand recording to you after the webinar concludes today. On your screen, you'll also see a Q&A chat window. If you have any questions, feel free to type them in there. We will try to get to your questions at the end of the webinar, and if for some reason we do not get to the question, we'll make sure to follow up with you directly. And last, we have a short survey at the end of the webinar. Please kindly fill this out so we can continue to improve our webinar. Your feedback is very important to us. Today's session is being presented by Carl D., Senior Developer Advocate at Azul Systems. He is a Java enthusiast and loves sharing and advocating Java-based technologies. Before we go ahead and get started, I actually have a poll question that I will bring up to help tailor the question. So I'll go ahead and launch this and then give you a few seconds to fill this out. All right. I'll go ahead and close and then share the results. And it looks like, yes, everyone's familiar with the callback, so that's great. Perfect. So then I will go ahead and hand it off to Carl to start the presentation so that we can go ahead and get started. Carl.
Great.
Okay.
Awesome. That's good to know about the poll questions because, everyone knows what a callback is. That's good. Hey, everybody. Nice to welcome back to the webinar series. Thank you for coming to this webinar on Deeper Dive. This is the last of the webinars of the 3-part series of Project Panama that's coming up in JDK 19. And if you've missed the first and second webinar, just go to azul.com under the Learn tab and click on Webinars on Demand or just search for webinars. Today we'll talk about callbacks. Really important. That's what the question was. Up to now, you've learned about Panama. If you've seen the previous webinars, the linker API allows you to do what is called a down call handle method, which allows you to create method handles to reference native functions. Now you're in this talk, we're going to talk about going the other direction, which is a callback where the linker has a method called the upcall stub, which actually creates a reference to a static Java method. So before we get into the talk, I just want to talk about Azul real quick. At Azul, we build high-performance Java runtimes that help customers reduce cloud infrastructure costs by lowering latency and increasing throughput. We have 2 JVMs to choose from. Both are derived from the OpenJDK and are TCK tested. We offer the community edition called Azul Platform Core or Zulu, a free version with the option of paid support, and Platform Prime, which is our optimized version that has the C4 garbage collector. It's a pauseless garbage collector. We have the Falcon JIT compiler that replaces the hotspot JIT compiler, and CNC, which is the cloud native compiler. It's a distributed JIT compiler using cloud resources. And we also have a feature called Ready Now, which allows for fast JVM startup scenarios. So head on over to azul.com/downloads to download and play around and see your performance gains. So let's get started. So here's the agenda. We're going to recap on the foreign memory access APIs from the previous webinar, and then we're going to talk about pointers, how they are represented in the native world and how we view them in the Java world in Panama. And then we're going to talk about callbacks and how they relate to the two worlds. And basically, to not get too far ahead of myself, but basically in the native world, they're called function pointers, as we'll talk about that later, where you can convert Java methods into function pointers so that your native code can actually talk to the Java code or invoke the Java code block. And then lastly, in the agenda, I'm going to demonstrate a callback using this Leap Motion device, which is a hand gesture recognition device. It's the game rock, paper, scissors, and this is where the game or the computer wins all the time. So to get all the code, the source code for the examples of the webinar series, just head over to my GitHub account, github.com/carld/Panama webinar. So there, all the code examples from the previous webinars are there, so just check it out. And of course, you can get the JDK. It's all available. The JDK, you can get it at azul.com/downloads and search for the EA release of JDK 19. I believe the latest builds are out today, so that image might be a little stale. The build 25 there. So again, another great news I just wanted to mention. A few days ago or last week, I believe, I think around that time, JExtract builds are now available from the guys at Oracle, the team that builds Panama. So they've separated the project of JExtract, so it's not bundled with the JDK. So you have to go download it from here, and all the examples, or most of the examples, use JExtract to simplify calling native functions. And so the instructions are at my the GitHub Panama webinar account. So the instructions on how to install it and everything are there. So you can go and download it. But also, just a reminder, they only offer right now the Mac OS, Intel, Linux, and Windows. I have an article at the bottom. It shows you how to build JExtract yourself as a tool for ARM64, you know, the Apple's new M1 chip or M2. And so you may have to build it yourself if you want to use JExtract for ARM64. So here, really quickly, just to point out, you want to set up your environment variables such as your Java home. And here I just created an environment variable called JExtract_home that when you download it, you decompress it into a directory. You would have to, you know, set the path for that. And then when you set the path for executing the tools like Java, Java-C, JExtract, I advise you to do it in this order. So set your Java home /bin and then your JExtract home /bin. It's really important because in the JExtract bin, it also contains a version of Java. So just so that there's no mismatch, and you want the Java version, the JDK 19 that you downloaded. So another dependency is the JavaFX modules or the JavaFX libraries. Here, our friends at Gluon HQ, they we can download the modules there, and you would also want to set up your class path. And the instructions are also at the Panama webinar account on my GitHub. Just to throw that out, as a convention, we often use the environment variable path2fx, and you just, wherever you downloaded it, you expanded it, make sure it says /lib on the end, wherever that directory is, and /lib. And then a lot of the scripts that are within the webinar workshop, the GitHub, the scripts actually reference and use that environment variable in order to run some of the examples, just for convenience. So just to keep that in mind. So again, there's the Panama webinar, the project for all the examples for this webinar series. Keep in mind, I just wanted to point out also that this particular webinar relies on GCC or your C compiler so that you can create your own library that you want to reference. So if you go to the README and you scroll to the bottom, the example for the example in this webinar is how to download your C compiler, install it, and then actually build the library for your operating system. So let's get started. Oh boy. So we're going to recap really quickly on the foreign memory access APIs, just like from the previous webinar. There's 5 steps. It's really simple. You obtain the memory session, you call the overloaded and many allocate methods, and you pass in a memory layout, and it returns a memory segment instance where it's, I'll explain later, where it's a pointer in memory with spatial bounds. And there you can use the get and set methods where they have an offset, and you also have get at index if you're dealing with an array of primitives. And so the last step is var handle, which is a really important class used to interrogate C structs or an array of structs. It's really handy when you pass in the memory segment instance. It can interrogate the fields within the struct. So, so again, here's a UML diagram with the derived classes for the primitive types, the value types, and the the predefined Panama value types, such as like Java _int or Java _float, and etc. And so the sequence layout, again, that's how you can take structs and turn them into an array of structs. And of course, the group layout, which is creating a struct using that class. So off of the allocate method, it returns a memory segment. So here are all the overloaded methods that allow you to create instances of things in memory or pointers in memory. So here's a whole bunch of them. You can create your strings, you can create your arrays. And so the third one is whatever the derived class, you can actually allocate it. And some of the other ones, you not only allocate it, but you can also set the value. That's where you see the second argument, which is, so you can allocate it and set the value. So here's just a simple preview of a simple C native struct. And then on the memory layout dot struct layout, it describes the native struct using the value layout, or the value layout, and the with name method to describe the fields within the struct. And the most important thing is the var handle class, which allows you to get and set values within the memory segment. So that's really nice. So, and last but not least is at the second webinar, I demonstrated with a JavaFX clock that instead of using the date time classes within Java, as a convenience, it's actually talking to a native struct that's defined in the time library on your platform. So within C, there's standard libraries. The time.h header is the library native to the platform to get your date and time. So this is just a demonstration on how to, utilize native functions. So, but of course, this is all about down calls. So, we're gonna, or down call handles. Now we're gonna talk about up call stubs, which is about callbacks. But before we talk about callbacks and such, we're going to talk about C pointers. We just need to understand some fundamental concepts in the native world, so that gives us a better understanding of like how the native library expects things to be. So when you convert things in Panama, so that the C ABI or the application binary interface of C understands that you're passing in what is expected as, a callback or a function pointer. So just to go through some fundamentals, what is a callback, or what is a C pointer? So what's a pointer? This is according to the actual guys that created C. This is the the K&R C programming book from Brian Kernighan and Dennis Ritchie, the late great Dennis Ritchie. So here it says C supports the use of pointers, a type of reference that records the address or location of an object or function in memory. Keep that in mind. Pointers can be dereferenced to access data stored at the address pointed to, or to invoke a pointed to function. That's really important also. Pointers can be manipulated using assignment or pointer arithmetic. We're only going to discuss about assignment. We're not going to be talking about pointer arithmetic as, not in this talk. So in the native language C, they have this concept of pointers. And so by the definition, what a pointer can do, a pointer can not only look at a function, but that which we'll talk about in a few minutes. But right now, this is about pointers to a variable in memory. So right now, this is nothing new. Here, you're just assigning a variable x to the value 5. But what's different about the native world than in Java world, that these primitives actually are stored in memory, and there's an address that you can that's assigned to it. So it not only creates a space in memory, but also you can obtain the address in memory. So here is a declaration of a pointer. The PTR is your variable name. It could be named anything. So there, the little star symbol on the left of it. So if you create a pointer, it has to point to the same type that where it's being stored. So like if it's pointing to X, which is of type int, it has to be of type int. So the pointer is not only just pointing to an address in memory, but that's the value that it's going to hold. And then, but it has to be the same type. So they use this operator, this ampersand operator, to obtain the address. So then it assigns that pointer, so it stores the address location of where X is at, if that makes any sense. So here's a visual representation of what I was explaining. So here, when you say int X, assigned to 5, it creates a space that holds the value 5. Since it's an int, it's probably 32-bit value. And then on the left is the address or the location of where the X variable is storing this 5. So then when you create a pointer, or you're declaring a pointer, it'll create a space. It's actually pointing to null, and it also has an address on the left. And so when you assign it the address using the ampersand, it actually will take that address, which is, cafe face, that hexadecimal value, the address of where 5 is, it'll be the value stored at that location. So how do you do this in Panama? So it's really simple, just like in the previous webinars. We take the memory session, we allocate space, we use the predefined value layouts like Java_int to represent the C primitive, because it knows the byte order and it does all the magic, and it knows how it's laid out in memory. And then it also assigns the value 5. So this is kind of like, or this is the way to actually create the variable X to store the value 5. And simply, this is pure Java, so when you create a memory address and the PTR, or the variable name, it's pointing to null right now. And then to actually grab the address location or the thing in memory, this is synonymous to the ampersand. You just call the method address, and it'll have a reference to it. And so later in the next slide, we're going to talk about how to actually go through the pointer instead of using X, the getters and the setters of X, but you're actually going through where it's pointing to. So it's very similar. But I want to just pause for a minute, and I just want to mention something that's really, really nice to know. I just want to mention a proposal that's in the works. It's probably going to come out in JDK 9 or JDK 20. So the idea is to take the memory address methods and fold them into memory segment, because really they're the same thing. The concept of a C pointer, the memory address class and the memory segment, they're kind of the same thing, because a lot of times when you talk about objects and references of objects, you're thinking of a reference like in Java, but in the case of the native world, it's really a pointer. But the difference in how it's viewed is when we describe it, a memory segment is a pointer with spatial bounds, and a memory address is viewed as just a raw pointer pointing to something in memory, regardless. So you can actually, with the memory address reference or instance, it's actually a pointer. So from the offset, you can actually, recreate a memory segment. So that's why the proposal, they'll combine it. They'll probably do away with memory address. Just keep that in mind. It's really nice to kind of collapse the two concepts, because they really mean the same thing. And it's just nice to know. So I just want to clarify that, because there's a lot of confusion when sometimes when you're in Panama, you don't think of it as a raw pointer versus a pointer that has spatial bounds. So like a raw pointer can actually point to null or nothing. So just keep that in mind. So like again, I said how we use a pointer in the native world. It's really a reference or an address in memory, and we want to obtain the value that's stored at that location. So here in this case, we created the pointer using the allocate method. We created space for it, or in this case it's null, but we called the address method to return the memory address. And here you can actually get the value from X because it's just a pointer. So when you say get the value layout and the offset, it'll take that 32 bits, it'll transform it into the Java world, and foo equals 5. So in order to set it, we're going through the pointer again, ptr.set, take the value type layout or value layout, you take the offset, it's 0 again, and then you want to set it to the value 10. So you're actually going through the pointer, not directly with the X, the memory segment of X. So in this output statement, it says x.get. Now you're actually using the X variable, and when you return or retrieve the value in the output, it is actually 10 because you set it through the pointer. Just something, if people aren't familiar with C, a lot of things it's all about pointers, and that's probably why a lot of people do not like C, because you can have a lot of memory crashes and things if you're not if you're pointing things in memory and you're going out of bounds, you can get a lot of errors. So now that you know about pointers, let's switch topics real quick, and this will come back because this is really important about function pointers and or callbacks. So again, up to now, we've learned about the linker's down call method to create method handles that reference native functions. Now we're going to go in the opposite direction, where we're going to, I kind of spoiled it, the upcall stub method so that method allows you to convert or take a Java function and pass that as a function pointer into a callback that's native. So what is exactly a callback? I'm sure everybody knows because of the survey. Everyone got it. So everybody knows what a callback is. So actually, I just want to kind of go over this according to Wikipedia really quick. A callback is also known as a call after function. So and is any reference to executable code that is passed as an argument to other code. That other code is expected to call back or execute the code at a given time. This execution may be immediate, as in synchronous callbacks, or it might happen at a later point, such as synchronous callbacks. And of course, in this webinar, we're just going to talk about synchronous. We're not doing asynchronous callbacks. And this is really important. Programming languages support callbacks in different ways. Often implementing them with subroutines, lambda expressions, blocks, or function pointers. So I just wanted to pause for a moment and just that sentence is kind of cool, because when it says, subroutines, sometimes that's referred to that in Python, and Lambda expressions or related to Java, and blocks might be Ruby or not or Groovy, and function pointers is really it's kind of more into the C and C++ world. So just kind of understanding the terminology when you hear these terms, they kind of mean the same thing when you're dealing with callbacks or callback behaviors, just to keep that in mind. But that last one, which we're going to go into, which is function pointers, that's the main talk, what it's about, because you're going to create these Java functions into native callback functions or function pointers. So here's a really quick example of a Java callback. This is just pure Java. You pass in a Lambda or a single abstract method into this function, and this function is the callback because it will call back the code block based on the definition. So in the body, the first statement is begin calling code block. It just outputs that, and then it invokes the code block using the run method. And so the last one is, that statement. So here's the Lambda expression or the statement as a runnable, and then you're just passing it into the callback, and then it executes. So here's the output. I just want to show you the execution order, which is kind of important because of the way callbacks work. There's a post invocation, something that is within the callback, and then it calls your code block that you passed in, and then it can actually do something else after the fact. So this goes into function pointers, which is the native way of callbacks within C. So by their definition, according to Wikipedia, I don't have to read this entire thing, but in a nutshell, it's really no more than a C pointer pointing to something in memory that references the location of where this function is. So just in the same context of a C pointer, where we had the example of getting the address of the X variable, it's the address of where X is actually stored. Here, in the same way, you use that ampersand, and I'm going to show you in a minute, you can get a reference to a function that's stored in memory. So functions are like first-class citizens. So very similar to some other languages where a function is a real thing and there's an address to it because it's stored in memory, and you just need a pointer to that function, and you're just passing that pointer to as an argument, and then the callback can actually invoke that function that it's pointing to. So in the native world, this is how you declare a function pointer. It looks just like a normal function, just like in a C pointer, how we declared it. We were the name of the variable, say it was X, and then we say we create a C pointer, and in this case, it's named pointer. In the same manner, it has to match the method signature of the function that it wants to point to. So this is a simple function that it's pointing to. It has a return type of void, which is nothing, return nothing. And then the name of the variable, it's called PTR, pointer. And it happens to be surrounded by this, paren, star, and the variable name, and then another paren. And that's just how you define a function pointer. But the rest of the method signature must match the function that you're pointing to. So then, of course, a function has function arguments, and this one has nothing. Here's another example where it returns an int, just giving you a little variety. And again, the function pointer name, I named it the same. And then function arguments here where it receives an int and a float. So nothing new here. This is just a native C function that returns nothing, and it takes no arguments. It's called my function, and it outputs this text. This is a normal C function. And so here's a declaration or an assignment of a function pointer, PTR, and you use, again, the ampersand symbol to take a reference or the location, the address in memory of the my function. So just to, I don't want to beat a dead horse, but this is, and sometimes function pointers are hard to read. And so in English translation, it makes sense in your mind when you start to declare these things. So here it says, declare a variable that is a pointer to a function named PTR. And it's pointing to an address location of a function named my function. So kind of get that flow in your mind so that sometimes it's nice to know what the language and what it looks like in the native C world. So sometimes it allows you, when you're in Panama, so you know how to create memory layouts when you use the memory session to allocate things. You have to kind of know what the C ABI or the C native world expects. So it's kind of important. It's nice to know the language and how it views pointers or function pointers and such. So again, here's the function pointer described again. The pointer is assigned to the address or where my function is located, and then it invokes the callback. The actual callback is my callback function, and you're passing in that function pointer. And so here's the callback. It accepts a function pointer. That's how it's declared, just like how you declared it when you passed it in. And it outputs something in the body, and then this is how it invokes it right here. Again, it has the paren, the star, the variable name, the paren, and then when you execute it, you use the two parens. If it has arguments, you pass it in, and that's where it invokes. So again, here's the output, and I just want to show you the order of operations or the order of execution, just to show you what callbacks everybody knows. The callback function is the guy that receives the function pointer, and then the function pointer is then invoked by the callback, hence the name callback. Let's do this thing in Panama. It's about time. So let's imagine a fictional library called mylib, and there's a function called callback func. So it accepts a function pointer, which is an address, location, or a symbol in memory. So on the Java side, I'm going to show you in a minute how you can convert a static method into a function pointer to be passed into the native function. So in step one, it passes this function into the function pointer. It turns into a function pointer in memory, and it passes it into the native function. Then in the body, it calls its native do stuff method, and then it executes your your code block that you passed in. So a really quick show of how the library was built, this fictional library that we created. If you have a C compiler, as you saw before, the code, it's located in a file called mylib.c, and the switches on, in the command line for GCC, it's -shared, which will generate one of these shared libraries. And the -o is an output of the actual file that it should be named. And for your particular operating system, if you're doing it for Mac, you would name it, you would have to prefix it with a lib. It's a naming convention, it's lib, and then your library name, mylib, and then the extension of dylib. And if you're doing it for Windows, there isn't the lib in front. You would have mylib, and then the extension would be .dll. And then for Linux, you would prefix it with a lib convention, and then the name of the library, and then the extension would be .so. So a really important thing, a lot of people get this confused, they don't realize it. A lot of times your library, your java.library path property should be set. If it's a third-party library, you want it in scope, you want it to be loaded for your Java application to actually use. So when you actually go to load your library, you use the system.loadLibrary method. I think I explained this in the previous webinars, but it's important because there's two locations. There's the library lookup from the default area, what your platform provides, and then there's the symbol lookup class, which has a lookup area, and this is where you look it up. And if that makes any sense. Yeah. So yeah, that's the symbol lookup will load that, and then you can actually reference it. And I'll show you in a minute. So here, really quick, this is really important. This is the key to converting a Java static method, that's Java code, into a function pointer to be passed into that native function on the left. So for instance, in the previous webinars, we talked about like printf, and we could use JExtract to actually generate bindings and actually doing it manually, where you can get a method handle referencing that native function. So that's nothing new. So we can create a method handle that references that native function that you see on the left called myCallbackFunction, and the argument is going to be the address, or the value layout would be address, the predefined, which is typically a pointer, right? So it's an address. That's what you want to pass in. So the 4 steps in actually creating a code block, or a executable, or a lambda, or a static function from the Java world, you want to convert it into the step 4, which is, or actually step 3, which is a native function pointer. Once you convert it to that, then you can actually pass it to the method handle that references the actual callback function. So step 1 is you create a static method. Step 2, you create a method handle that references that static method. Then step 3, you convert that method handle into a native function pointer, so that it's in memory and it has a pointer to it, so it's a memory segment, and that's what you pass into the method handle that references the native callback. So really quick, this is what we've seen before, which is the C callback function natively. And again, the symbol lookup is the area where you have third-party libraries. If you have the java.library path set so that the library is loaded, it looks it up. It's an optional object, and inside it, it shouldn't be null. So when you call the get, it should return a thing in memory or a pointer in memory with wherever that function is, it's assigned to callback. So it should not be null if it's loaded properly. So here is, yep, it's pointing to the native function. So once you have it, you now have to create, this is step 2, you create the method handle, or no, I'm sorry. This is just creating a standard method handle to the native callback. That's it. Like what we learned in the first and second webinar. So this is how you describe it. It takes the of, it uses the of void method. It implies that it doesn't return anything. And the argument is an address, which is a pointer. It's a function pointer, to be specific. So here is how you invoke it. Now, what it's passing in is actually a memory segment of the call me please function pointer that we're going to create with the 4 steps that I'm going to show you. So remember, the 4th step is really this invoke right here. So we're I'm gonna show you the steps 1 through 3 that actually creates that call me please FP object. So again, it's a memory segment when it's all said and done, when you convert a static Java method into a function pointer ready to be passed into the that invoke that we saw before. So again, here's the steps. You create a static method, you create a method handle, and so here, step 1, you create a static method. Here, we're still in the C world, kind of, because we're using Panama code to actually create a C string, and we're using the printf method. I use JExtract to make it convenient. We're just passing that in to output into the console. So this is new. So step 2, you want to create a method handle referencing that static method in Java, the call me please method or the static method. And so there's a method handles.lookup, and there's a method called find static, and you can pass in the class of where that static method is located, and there's the name, and then the last is what it describes the method return types. So nothing, it's very straightforward. It looks like how you created a down call. It's similar when you create a down call handle method. So third and final step, which is the key to all this in the entire talk, is actually converting the static method from a method handle to a actual thing in memory or a pointer in memory to be a function pointer, so that it follows the CABI that allows you to call the callback, the native callback. So this is very similar to the thing you see on the bottom, which is the declaration of a function pointer. The variable name is PTR, and it follows the method signature also. So it calls the linkers.upCallStub method, and then you pass in the previous step, the callback or the call me please method handle, and then the function descriptor. And then you also have to pass in the memory session as the last. That's the only thing. So the 4th step, we talked about that in the earlier step or the earlier part, is now you can now invoke it, and it'll pass in your function. It thinks it's a function pointer, a native function pointer, and it will start invoking it. And then it'll invoke that callback for that, because the method handle is referencing that callback, and then you pass in that memory segment. So here's the output really quick. Again, I just want to show you the order of execution. So it calls in from it outputs the body from the callback itself, and then it invokes your Java static method, which is kind of cool. So really quick, I'm going to have a demo. So this demo uses the leap motion device, or it's a gesture recognition device. So leap motion. So what I did is I created a demo of rock, paper, scissors, which I will explain in a minute. So this leap motion device is created by ultraleap.com. They renamed their company. And so I have this device, and I've had it since they came out. So I'm using this library since 2013. So I'll explain about that. But Ultraleap builds hardware devices capable of haptic feedback and gesture recognition, which is the leap motion device, and typically used in games and VR type applications and such. So with the leap motion, I created a simple rock, paper, scissors game. However, in this scenario, the computer always wins because, it's very fast. It kind of cheats, and I'll explain. So if you've ever played the game as a child, you would typically say 1, 2, 3, shoot, and you would use the gesture like 1, 2, 3, shoot. And at the same time, both players, they would throw their gestures. It could be a rock, it could be a paper, or it could be or scissors. And if the device will detect your right hand or your left hand and how it's tilted, it could even detect other people's hands if somebody threw their hand in the view. So it would detect the number of hands, the hand, and then it can also detect the bones in your hand, which is kind of interesting. But they also have a convenience method that detects the number of fingers. So if you have 0 fingers, your hand is extended, it means you have a rock. And if you have a hand that's extended and you have 5 fingers, that means it's like it represents the paper. And if you have like the scissors or the peace sign like this, it represents 2 fingers, it's scissors. And so because, in the initial process, you're passing in your Java side, it's represented as a function pointer or your Java code, and it's passed in to that listener, and then it would actually invoke your function on shoot. So on the left, just to go through the process real quick, the device can detect frames upwards of like approximately 100 frames per second. So it's very quick in detecting your hand movements and such. And then once it detects those criteria, it then invokes your callback or invokes your function pointer on the Java side. And of course, what's great here, on the Java side, it's a Java FX application that shows an image of the opposing image. So if it's 0, which means a fist or a rock, I'm sorry, and it'll show paper. So it'll win because it's the opposing image. So if it's paper, it'll show scissors. If it shows scissors, it'll show a rock. So it's so quick, that's why it appears that it wins because your eye cannot catch how fast it can detect your hand gestures, so that's why it always wins. So let me turn it over to Jenny just to show you the demo and how the code or the application works. So there you have it. So really quick, I just wanted to show you, I know we're out of time here. Not sure how much time we have left, but really quick, I just want to show you the application layers. The library is actually C++, and I expose following the CABI, there's a way in C++ to actually expose things as a C function. So that's really important to know. That allows Panama to actually talk to the library because I'm exposing that as a C function, and then it actually does the callback. So again, it's super simple code. You create the static method here. It takes the number of fingers. Again, we've done this before, and then there's I use a web or an image view. And then I have a function that it's a map that gives me the opposite of whatever the human player actually gestured. If it's a rock, it'll produce a paper, or the vice versa. So here's how you expose. So that looks like an ordinary C function. I know it looks a little bit different here. There's something called a const void pointer. It's no different than, it's like an any type, but it's a pointer in memory. It's just easier to do. I mean, we could have passed it in by value. It could have been an int, but here I just chose to do it this way because in the C code, it actually passes a reference to the value of the int. So here's you just declare it just like a C function, and then you prefix it with this this keyword called extern quote C, which exposes it as a C, so a C function. So this allows other languages that understand the CABI to actually just call this library. So then there's so this is C++ code, and here it's instantiating by passing in the function pointer into the listener, which listens on a separate thread, listening for approximately 100 frames per second. And here's the frames as they are recognizing the hand, and then it takes the fingers, and then it executes your callback. So again, this is nothing new. This is the 3 to 4 steps of creating and looking up the static method, turning it into a function pointer in memory, the memory segment instance, and then you invoke it through the reference to the method handle to the native callback, if that makes any sense. So those are following the steps, and it's that easy. So there we go. And here's some references. I just want to point out in the third bullet is more information on how to expose functions in a different language, in a foreign language. such as C++ or Swift or Python, so that Panama can actually talk to this. It thinks it's a C function, so so those articles would you might find interesting. So that's all I have. Whoops, I'm sorry.
Thanks, Carl, for a great presentation, and thanks everyone. I know that I want to go ahead and just get to one question. I know Rajiv had sent over this queue question, so I wanted to make sure that, Carl, you had a chance to answer it. He did ask, how does the API use X when referring field in struct? Is there a way in API to introspect the field names in C struct?
I'm sorry, can you repeat that again? I'm sorry, I didn't catch it.
Sure, yeah, no worries. How does the API use X when referring fields in struct? Is there a way in API to introspect the field names in C struct?
Oh, that was in the, I believe we're talking about using var handles, and actually you have to define var handles to, if it's defining a C struct, it knows how to interrogate a memory segment instance. So you pass in the memory segment instance into the var handle that you created, so it knows how to pull out the fields. I think that's what they're trying to say.
And I think Rajiv, he wrote that it was in the beginning of the presentation while we did the recap. Did that answer the question, Rajiv?
Yeah, in the beginning, we kind of explained that in the recap about structs. I hope I'm answering that properly. Not sure.
No worries. Great. And then I'll go ahead and see if there's any other questions. I don't see anything else, so I think that will conclude our webinar today. Again, thank you everyone for joining us. Thanks, Carl, for a great presentation. Feel free to make sure that you fill out our survey at the end of the webinar. We want to make sure that we are continuously looking to improve our webinars, so appreciate your feedback. And again, we'll send over the recording for this webinar as well as the other two, and appreciate the time today. Thanks, everyone.
Thank you.